Sir, can I say questions?
Yeah, yes, please let me know.
Omega be non-empty open connected subset
Okay, wait.
of C.
Okay, so your omega is non-empty. Or just wait, I think I left the meeting or somehow. Wait. Yeah, just wait for a few minutes. I think I have left the meeting somehow. Let me check. Sorry. Hello. Hello. Yeah. Darshan, just wait for 5 minutes. I think I have somehow left the meeting with my iPad, so I will just join. Okay. Yeah, just wait for a few minutes. Now it is. Yeah, now you can see.
Omega be non-empty open connected subset of
Yeah, non-empty, open connected.
open connected subset of C.
Okay, open connected subset of C. Okay, so basically a domain in C which is non-empty. Yeah.
And F be holomorphic function on omega.
Yeah.
And F is not equal to 0.
F is not identically equal to 0, na?
Identity equal to 0.
Yeah.
And Z equal to Z belongs to omega set है Z equal to नहीं Z belongs to omega Fz equal to 0 ये set में है.
Okay, so collection of all this set where F is
Fz
0.
equal to 0.
Yeah.
With the zeros of F in omega,
Yeah.
then F does not have limit point in omega. ये ट्रू है या false है ऐसा पूछा है तो.
Yeah, so this question we have already discussed in the previous assignment, week 7 assignment or week 6 assignment. So basically, this is basically not true, because if it has a limit point, then f has to be identically equals to 0. This will gives a contradiction. Okay.
If it has limit point, then it is identically 0.
Yeah. So that is the identity theorem, isn't it?
Okay.
Yeah. Like we have discussed this in previous assignment.
Okay, sir.
Yeah. So I will just start the Week-8 assignment. So Darshan, please mute yourself. I will start now.
Okay, sir.
So hello everyone. Good evening to all. My name is Abhishek Pandey. I am a Prime Minister Research Fellow in the discipline of Mathematics at IIT Bhubaneswar. So today we are going to discuss about Week-8 assignment. This is basically on Schwarz reflection principle, winding numbers, and other things. So let us start. So let us see. This is the first question. So which of the following statements are true? Okay. So basically your omega is a domain. Okay, means open and connected. Let f says that omega to c be a continuous function omega such that this happens, like integral of f over every closed curve is 0, then f is holomorphic. Okay, so this we have already seen in the next previous assignment. Okay, so this is true. So option 1 is true. This we have already seen. So can you tell me like how we have how we have done this question? This we have discussed in the previous assignment.
Inverse of Cauchy integral theorem.
Can you be more precise? So this, to show that f is holomorphic, what we have done? So basically we have shown that for if f is a continuous function omega and integral over gamma f equals to 0 for every closed rectifiable curve gamma contained in omega, then we have shown that f has a primitive, isn't it?
Yes, sir.
Yeah, so means there exists f such that fz equals to fz for all z belongs to omega. Okay.
Okay, sir.
Now this capital F is holomorphic. So f dash is also holomorphic. Okay, this implies f is holomorphic. Okay. Now let us look at the second question. So this we have done, like you can see in the week 7 or week 6 assignment, it is there. Like we have shown that if integral over every closed curve, closed rectifiable curve is 0, then basically that function has a primitive. Okay, so this we have done. Now let us look at the second option. So the second option is, it is asking f such that omega to c is continuous such that integral of fz equals to 0 for every triangular path. Okay, means on every triangle, for every path in omega. Okay, then f is holomorphic. So this we have to check. So this statement is true. So we will see the proof. Okay. So what we will do that. So basically this is Morera's theorem, isn't it? So this is also known as Morera's theorem. So what we will do that, first we will show that f is holomorphic in every ball. Okay, every ball contained in omega with center z and radius r. Okay, So for this we shall show that f has a primitive in basically every ball. Okay, so consider any ball basically centered at z0 and radius r contained in omega. Okay, and define, so these things with the technique we have already discussed. Okay, how to define the primitive. Okay, and define f such that ball z0 to r to c by f of z is basically a line segment z0 to z, f of z. Okay, this is clear. Like in ball we will define, like from z0 to any point z, we have a line contained in that ball. Okay, now so here observe that for any point z1 belongs to omega, we have f of z is basically z0 to z1 fz dz plus z1 to z fz dz. Okay, so like basically you have a domain like this. So at z0 we are considering the ball which is contained in that domain. So this is omega, this is your ball. So at any point we are just taking this integral. Okay, and if you have any other point z1 and we go like this, okay, so this will be, so this integral can be written as this plus this. Why? Can anyone tell me? Hello? Hello?
Yes, sir.
So can anyone tell me how this is equal?
प्लस इंटीग्रेशन z to z0 भी होगा ना सर?
सॉरी,
ये कैपिटल fz इक्वल टू आपने लिखा ना इंटीग्रेशंस में z0 to z1 z1 to z0 नहीं होगा?
No, actually what I am doing is, so basically what is fz? Fz is z0 to z. Okay,
Yes.
so basically this integral is equal to this integral. Why?
Okay, sir.
Because once you consider this triangle, okay,
Yes.
so over this triangle integral will be 0, isn't
Yes.
it?
Yes.
Yeah, so over this triangle integral will be 0. So once you do that z0 to z1, sorry, z0 to z, z to z1, z1 to z0, so this integral will be 0. Okay,
Okay, sir.
so this integral will be this plus this.
Okay.
Yeah. Okay, so now our claim is basically f dash z1 is small f of z1. Okay, so now what we will do is, so we will calculate this one. z1 upon z minus z1 minus f of z1. Okay, so what will be this? So this will be 1 upon z minus z1. Okay, now what is your f of z? Okay, so f of z you can write like this one. Okay, so this will be
Integration.
Integration z0 to z1 f of z dz plus integral z1 to z f of z dz. Okay, and simply this one f of z1, so this will be z0 to z1 f of z dz. Okay, minus, so this you can write it as what we can do is that, so f of z1 dz, okay, z0 to z1, okay, and z minus hello, this is clear? Wait, let me write it here clearly. So this you can write it as okay, so this is clear, this one. So f of z will be out, and this integral will be z1 minus z0, and this will be cancelled out. Okay.
Okay, sir.
Yeah. So now this is nothing but, so now z minus z1. Okay. So as you can see, this term and this term will get cancelled out. This term and this term. Okay. So this will be integral z1 to z f of z dz minus integral z1 to z f of z1 dz. Okay, so now this is nothing but z minus z1. So this will be integral z1 to z f of z dz. Okay, sorry, this will be f of z minus f of z1 dz. Up to this is clear?
Yes, sir.
Okay. So now once you take the modulus, it will come as f of z minus f of z1 upon z minus z1 minus f of z1 is basically less than equals to f of z minus f of z1. Okay. So as z tends to z1, we know that f is continuous. So fz will tend to f of z1. So this will give limit z tends to z1 f of z minus f of z1 upon z minus z1 is basically f of, okay, that is f dash z1 is f of z1. So f is morphic on each ball contained in thus f is holomorphic on omega. So this is clear?
Yes, sir.
Okay. So let us look at the third option, this one. So basically one is true, okay. So one is true, two is true, third one is basically false. We'll see this one, and let us look at the third option. So so basically what third option says, let Fn be a sequence of holomorphic function defined on omega converging pointwise to a function f on omega, then f is holomorphic. Okay, so this statement is false, but something is true which is less known. Okay, so this statement is false, but so I will mention a theorem of Osgood. Okay, which says that, so let's see it. So let Fn be a sequence of holomorphic functions on omega, okay, such that Fn converges to f pointwise. Okay, so basically this f is not holomorphic on whole omega, okay, but this theorem tells us that there exists some set which satisfies some property, there f is holomorphic. Okay, so I will just write it. So this paper basically got published in Annals of Math. There is a paper of Osgood, in this it is there. So Fn converges to f pointwise, then there exists an open dense set in say D contained in omega such that f is holomorphic. Okay, now let us look at the option 4. So this option is true.
सर एक बार फिर से थॉट दिखाइए ना.
Yeah.
Okay.
So
Okay, sir.
yeah, so it says that let Fn be a sequence of holomorphic function on omega. Like we know sequence of continuous function converges pointwise to a function, then we cannot say that f is continuous, isn't it?
Okay.
Yeah, so this is same as that one, but this theorem tells something more about the function. Although it is not holomorphic, but there exists a dense open subset where it is holomorphic. Okay.
Okay, sir.
Yeah. So now let us look at the next question. So Fn says that omega to c let be a sequence of holomorphic functions such that basically Fn converges to f uniformly on omega. Okay, so since Fn converges to f uniformly on omega, clearly f is continuous. That we know from real analysis. Now to show that f is holomorphic, we will use Morera's theorem. Okay, so you can let T be a triangle. Let T be a triangle. Let T be a triangle in this omega. Okay. So Fn converges to F uniformly on T also. Okay. This is clear?
Yes, sir.
Okay. So what we will do is, wait, let me write it in another way. So let T be a triangle in so what you do to show that it is holomorphic, first we will show that it is holomorphic in every disk. So consider any disk. Consider any disk D in omega, okay, and any triangle T in D, okay.
Yes, sir.
Now Fn converges to F uniformly on T, okay. So limit n tends to infinity Fn z dz over T is equals to basically T f of z, isn't it?
Yes, sir.
Okay. And what is this thing? So this will be 0.
No, yes, 0.
Okay. So why this is 0? Cauchy's theorem.
Cauchy's theorem.
Yeah.
For triangle.
Yeah. So Cauchy's theorem from triangle. So basically this is 0. Okay. So F is holomorphic in D, and hence since D is arbitrary disk, let me write, and since D is any arbitrary disk, F is holomorphic in. So this is clear?
Yes, sir.
Okay. So let us move towards the fifth option. So this is also true. Let us see what is the fifth option. So this is true. Okay. Yeah. So let us look at the fifth option. So suppose D plus. So D is the unit disk. Okay. So suppose D plus is the collection of all those points whose imaginary part is 0 in the unit disk, and D minus is collection of all those points whose imaginary part is less than 0. Okay. And F is holomorphic on this one and continuous on D. Then we need to check F is holomorphic on D or not. Okay. So this is true. Like F will be holomorphic. Let us see. So basically what it is. So let me draw a circle. Okay. So basically in this one. So this is your D plus, okay, and this one is your D minus, okay, and this line is your real axis intersecting with that one. So combining, so let us consider this, so let us say this is I, okay. So basically so basically D is nothing but D plus union D minus union I, okay, and F is holomorphic on D plus and D minus, okay, and continuous on D, okay. So we need to check that whether F is holomorphic on D or not. So question is, F is holomorphic on D, okay. So again we will use Morera's theorem. So for that, so see, if we take a circle here, triangle here, so what will be the integral of F on this triangle?
0.
Yeah, good. And what will be if we take in this one?
0.
Yeah. So only we need to worry about triangle of this type, such that one
Yes.
side is on this one, okay, and of triangle of this type, okay, such that one vertex is on this one,
Okay.
okay. So we will see here, so what we will do, we first look at triangle of such type, okay. So this is your A, B, C, okay. So I will, so what I will do here, I will make some delta distance. So this is your delta, okay. So this is your A, B, C, and let us call this one as B delta, and this one is as B delta dash here, and this one is as C delta dash, and this one is C delta, okay. So now let us start. So first observe that mod of fz is less than equals to m, okay. Wait. Let me write it precisely. We can always construct a compact set K such that this triangle is contained in K, isn't it? And since F is continuous, mod of fz is less than equals to m for all z belongs to K. So basically what we are doing, we can always construct some compact set, okay, like this, so that this triangle will be inside, okay. And on this compact set with all this covering, on this function will attain the maximum, isn't it? Hello?
Yes, sir.
Okay. So up to this everything is fine. what we will do now, now consider the integral of ABC, integral of fz over ABC. So this is nothing but a b delta c delta, okay, fz dz plus b delta bc c delta fz dz. Okay, so basically what is a b delta c delta? So this one over this, okay, and then over this, okay. So over ABC, if you have to do the integration, so ABC will be union this and this. Clear?
Okay.
Yeah. Now this one is 0. Why?
Cauchy integral.
Yeah, so this one is 0 by Cauchy's theorem. Okay. So and now, so this integral ABC fz dz is basically equals to b delta bc c delta fz dz. Okay, since delta is arbitrary, okay, so this we can write it as fz dz is equals to limit delta tends to 0 b delta b c c delta fz dz. Now we have to compute this integral. Okay, what is this? So b delta b c c delta fz dz is nothing but b delta b delta dash fz dz plus integral fz dz b delta dash c delta plus c delta dash c fz dz. Okay, so what is, so basically we need to calculate this integral. Okay, so what we are doing is we are calculating from b delta to b to b delta dash, and then this one. Okay, then b delta to b delta dash to c delta dash to c delta, and then this. Okay, and c delta to c delta dash, this to this to this. So we are doing 3 integration. Clear?
Yes, sir.
Yeah. So observe that as delta tends to 0, length of b delta dash tends to 0, and length of c delta dash c tends to 0. Okay, so this you can observe. Basically, as delta tends to 0, length of b delta dash, like this one, so this one tends to 0. Okay, as delta tends to 0, and hello,
Yes, sir.
and c delta, this
C
one,
delta.
yeah, so as delta tends to 0, this also tends to 0, this length. Okay,
Okay, so only rectangle is remaining.
yeah, so only this part is remaining. Okay, so when length tends to 0, you can estimate, like what you will do. So thus we have integral b delta dash fz dz modulus is basically less than equals to, this will be supremum of, this I should write m into length of b delta b p delta dash. Okay, and this tends to 0. Okay, so this will be 0, this integral. Okay, and similarly, so this implies integral b delta b delta dash fz dz is 0. So similarly, integral c delta dash c fz dz is equals to 0. Okay, now the only thing is this integral. So integral over b delta dash c delta fz dz. So this we can divide into 4 parts, like 4 sides. Okay, so integral b delta dash fz dz plus integral b delta dash c delta dash fz dz plus integral c delta dash c delta fz dz plus integral c delta b delta fz dz. Okay, now
Yes, sir.
now as delta tends to 0, length of b delta dash tends to 0 and length of c delta tends to 0. Okay,
Okay.
also this integral b delta dash c delta dash fz dz plus c delta b delta fz dz, this summation tends to 0 as delta tends to 0. Why? So as delta tends to 0, this one, as delta tends to 0, this b delta will become bc, isn't it? Oh, sorry, not bc. B delta dash c delta dash. Okay, now you just take delta tends to 0, so this line will be here. Is it clear?
No, sir.
See, let me just write it down. So this will be like this and this and this. So like if I reduce our delta, like if suppose if I take delta this one, so what will be b delta dash is b delta and c delta. Okay, so this will be here. Okay, so b delta dash will be here, isn't it? If I reduce to
Yes,
delta
sir. Yes, sir.
delta like this, so this will be here and this will be here. So now you have to do the integral on this one, then on this one. First this side, then this side. Okay?
Okay, opposite side. So,
Yeah.
integration.
Yeah. So this will be 0 at delta tends to 0. So combining all this, we have fz dz is equals to 0 over abc. Okay, so by Morera's theorem, f is holomorphic. So this is clear?
Yes, sir.
Okay. Okay, let us move. Okay, first let me charge this one. Wait. Yeah, just wait for 1 minute. Let me. सुखदीप, सुखदीप, थोड़ा वो दे देना तो उसका वो रामकरण का वो रामकरण का एक्सटेंशन जल्दी लाना. इसमें लगा वहाँ पर होगा. अरे क्या निकाल दिया? अरे वो निकाल क्यों दिया भाई? वहाँ लगा दो. हो गया? Hello? So,
Yes, sir.
Yeah. So let us move towards the second question. So it is regarding the winding number. Okay. So basically, if gamma is any curve, so write the winding number. So if gamma is any curve and z dot does not belongs to gamma, so this is nothing but winding number dw upon w minus z. Okay, clear? So basically winding number
Yes, sir.
yeah, so geometrically we can say that winding number of a point with respect to a curve is basically how many times curves encircle that point, okay, moves around that point. Okay, so geometrically that is the meaning of like if you take the unit circle, if you take the unit circle and take the point, so for this point winding number is 1, like unit circle moves once around this z naught. Okay, so this is 1. So this is the geometrically. So let us look at the first option. So winding number is invariant under reparameterization. Okay, so this is true because this integral of a function is always invariant over the parameterization, isn't it? Like we have seen this in, I think, week 4 assignment. Okay, is it clear?
Sir, invariant के लिए
Like yeah, so suppose you have a curve gamma and reparameterization. Reparameterization is gamma dash. Then basically we have to show that is winding number of z with respect to gamma is equals to winding number of z with respect to gamma dash. So basically what is this? This is nothing but this integral. And we know that integral is invariant under reparameterization.
Yes, sir.
Yeah, so this is true. So look at the second option. So second option is false. So what is the second option? So this is for a closed curve gamma and z not in the image of gamma. We have this one. So in the earlier days, what we know that integral over gamma fz dz is equals to fz dz. This one is minus sign, isn't it?
Yes, sir.
Yeah. So this is false. Okay, because there's this should be equals to minus of. Okay.
Yes, sir.
Now look at the other option first. So let us look at the fourth option. So this we already know. Okay, like so basically winding number is just an integral, this one. Okay, so integral over gamma 1 plus gamma 2 will split on gamma 1 and gamma 2. Okay, so this is also true. These all the integral properties we have seen in the previous assignments.
Yes, sir.
And also the and also this integral is holomorphic in C minus Z, isn't it?
Yes, sir.
So if you take any homotopic curves on C minus Z, so this integral will be same.
Yes, sir.
Yeah, so by that property this is also true. Now this is the most important property, that winding number is locally constant function. Okay, so let us look at the third option. So basically third option is true. Okay, let gamma such that 0, 1 to C be a closed curve. Okay, so winding number from C minus gamma to R, so let us set it C only. We have to show that this is a locally constant function. Okay. So what is the definition of this one? Z is basically 1 upon 2 pi I integral over gamma dw upon w minus z. Okay. So what I will show that so what I will show that this is a holomorphic function. Basically this is differentiable function on this one. Okay, this is a differentiable function on this one. Okay, so let z naught, okay, so let z naught be any other point. So you consider this one, w of z minus w of this upon z minus z naught. Okay, so what is this? So basically I will show that our claim, let me write our claim. So for any point this is this. Okay, so basically our claim is z naught is nothing but integral 1 upon 2 pi I integral over gamma dw upon w minus z naught whole square. This is our claim. Okay, so basically the derivative will look like this. Okay, so now consider this one. Okay, so what is this? This is nothing but 1 upon z minus z naught. Okay, this one will be gamma dw upon w minus z minus integral over gamma dw upon w minus z naught. Okay, now once you calculate this one, you will get 1 upon z minus z naught. So this is nothing but w minus z naught minus w plus z upon w minus z into w minus z naught to dw. Okay, so this is nothing but integral. So this is nothing but dw upon w minus z upon w minus z naught. Okay, this one is clear?
Yes, sir.
Yeah, so now we will consider this one, z minus w gamma z naught upon z minus z naught minus integral over gamma dw upon w minus z naught square. We will consider this value. Okay, so basically what we will prove that this tends to 0. Okay, when z is sufficiently close to z naught. Okay, so what is this? This is basically integral over gamma dw upon w minus z naught minus integral over gamma dw upon w minus z naught square. Okay, so I am just ignoring 1 upon 2 pi I. Okay, because it will not make any difference. Okay, this is dw. Now what is this? So this will be integral over gamma. This will be w minus z into w minus z naught square. Okay, so this will be w minus z naught minus w plus z. Okay, dw. So this will be equal to, so z minus z naught will be outside. Okay, so this you can write this, and integral over gamma dw upon w minus z into w minus z naught square. Okay, so basically so here w is on gamma. Okay, so since w is on gamma, so we can always find an r such that mod of w minus z is greater than equals to r, and mod of w minus z naught is greater than equals to r. Okay, is it clear?
Yes, sir.
Okay, so once you do this one, this will be less than and equals to this quantity, this one. So this will be less than equals to mod of z minus z naught upon r cube mod dw. Okay, and this tends to 0 as z tends to z naught. Thus so what we will get? Z naught is nothing but 1 upon 2 pi I integral over gamma dw upon w minus z naught whole square, isn't it?
Yes, sir.
So up to this everything is clear.
Yes.
Okay. Now your C minus this one, this is always an open set, okay, isn't it? Hello? Hello?
Yes, sir.
Yeah, so this is an open set. So it can be written as the countable union of disjoint components, isn't it? Disjoint connected components, okay. So what we will show that, so if Z naught belongs to U, one of such component, okay, so W gamma dash Z naught is what? Integral over 1 upon 2 pi I integral over gamma dw upon W minus Z naught square, okay. Now observe that this function 1 upon W minus Z naught is holomorphic. So let us write it as capital F Z, FW is holomorphic on C minus Z naught, okay. And what is its derivative? Isn't it?
Yes, sir.
Yeah. So basically what does it mean? This this function has a primitive in C minus Z naught, isn't it?
Yes, sir.
So what will be this integral? So suppose you have a primitive of a function. Yeah.
Zero.
Yeah, so this integral will be 0, okay, because your gamma is a closed curve. So this implies this integral is nothing but 0, okay, fine.
Yes, sir.
Yeah, so so this integral is 0. So what does it mean? W omega is constant on each component of, okay, that is, it is locally constant. Is it clear? Because this is a very important property of a.
Yes.
Yeah. So let us look at the third question. So for third question, you have seen in the, in the lecture notes or classes of this one, this theorem. So first I will mention this theorem. So let f such that omega to c be an analytic function, okay, and there exists a point z naught belongs to omega such that f dash z naught is not equals to 0, then there is r greater than 0 such that f is 1 1 on the ball centered at z naught and radius r. So this theorem you have seen. Isn't it? So once the derivative is non-zero at some point, f is locally 1 1 around that point, okay. This is clear? Rajesh, is it clear to you?
Clear, sir.
Okay. So now let us look at the first option. So it is asking whether first option is locally invertible around every point. So first option is true. Okay, in C minus 0. So basically what is f dash z? 3z square.
3z square.
So it is non-zero for every z belongs to C minus 0.
C minus 0.
Okay.
Yes, sir.
So according to our theorem, f is locally invertible. So f is locally 1 1 means it is locally invertible. Okay. So this is true. Now let us look at the second option. Fz is equals to z square is a 2 to 1 map in the punctured disk. So this is true. So you take any point z1 and take minus z1. Both will go to the same point. Isn't it? So option 2. So basically option 2 is also true. So you take z1 belongs to d 0 comma r. What is this? Minus 0. Okay. So minus z1 is also belongs to this one, isn't it? Because mod z1 is less than r. So mod of minus z1 is also less than r. Okay. And f of z1 is nothing but f of minus z1. Okay. So this is true. F is a 2 to 1 map. Now let f be an entire function which is locally invertible at every point in the complex plane. Then f is invertible on C. So this is not true. This is false.
Sir, I have one question. Fz equal to z square, तो f dash z is also not equal to 0 है, तो ये theorem apply नहीं कर सकते?
Yeah, so basically this theorem tells us that there exists a neighborhood around that point where it is 1 1.
Okay.
Okay, so as you said, z square derivative is 2z and this is non-zero in this domain. Okay, so
Yes.
for every point there exists a neighborhood where it is 1 1. Okay, but we cannot say that it is 1 1 in the whole domain.
Okay.
Yeah, for every point there exists a small neighborhood where it is 1 1. Like you can in the next example you can see. So the third one. So third one is false, and your example is e to the power z. Okay. So basically this is, so f dash z is e to the power z, which is non-zero for all z belongs to C, but f is not invertible, not 1 1 on C. Clear? Whether this thing is clear or not?
Yes, sir.
Okay. Rajesh, to you it is clear? Okay. Now let us look at the last option. So let me draw a line. So this and this. Okay. Yeah. So last option is saying fz is equals to this, maps f maps upper half plane onto the unit disk. Okay, so this is true. So what you need to do is, so your map is f of z is equals to z minus I upon z plus I. Okay, now as you can see, you take 0, 1 and infinity. So you just take the orientation of real line. Okay, so you are walking on this real line in this direction. Okay, so you just so 0, 1 and infinity. Okay, so now under this map 0 goes to -1, so -1 is here. 1 goes to minus I, this you can check, okay, and infinity goes to 1, okay. So this orientation we are getting. Now by the orientation theorem for the Mobius transformation, by orientation theorem, this theorem you can see in the Conway book. Let me write the reference here. So by the orientation theorem for the Mobius transformation, this left hand side part, this part, will map to the left hand part of the other circle, okay. So once you take the orientation like this, so what is your left part, what is in your left side? It's the inside of the circle, okay. So basically the upper half plane maps to this one. Is it clear? This question
Yes,
is
sir.
okay, nice. Now let us look at the fourth question. So basically it is solution. Just look at the first option, okay. So first option is so as you can see that this option is true. The question is, this function is holomorphic on the upper half plane but not on the lower half plane. So the only point is minus I, and minus I lies in the lower half plane, okay. So this is true. Now let us look at the second option. So f is holomorphic function on the right plane, okay. So f is holomorphic on the right plane and continuous on the imaginary axis. Continuous on the imaginary axis. Okay. Then f is entire. So can anyone tell me the Schwarz reflection principle? So here we will use the Schwarz reflection principle, okay. So I will just give the idea. So what you do, so the Schwarz reflection principle you can see in the YouTube video, like of this PMR for NPTEL for the Week-8. You see the So there Schwarz reflection principle is mentioned. So from there you can see the statement, okay. So now you have to consider that H plus. So this is the upper half plane to C, defined by Zz is equals to I f of minus Iz, okay. So once your Z belongs to upper half plane, minus Iz belongs to where? So basically Z belongs to H plus, that is Z equals to x plus Iy, where y is positive. So what will be Iz? So it will be minus y plus Ix, okay. That is, oh sorry, it will be y minus Ix, isn't it? Where y is positive, means minus Iz has positive real part, okay. So minus Iz belongs to Please let me know. Darshana, Rajesh.
यस सर, इतना समझ में आ गया.
Hello.
यस सर.
Yeah, so if z belongs to upper half plane, so minus iz belongs to right half plane, isn't it?
ये समझ में नहीं आ रहा सर.
Okay, wait. So see, z is in upper half plane. Okay, this one is clear to
Yes
you.
sir.
If upper half plane, then imaginary part should be positive.
Okay.
Now what will be minus iz?
Y minus ix.
Y minus ix. So what is the real part of minus iz?
Y.
And what is y? Positive.
Positive.
So real part of minus iz is positive. So minus iz is in right half plane.
Yes, right half plane.
Okay. Clear?
Yes.
So this is defined. Okay. So since f is analytic, g is also analytic. G is analytic in upper half plane. Okay. Now what will be the, if z belongs to R, what we can say about gz? Can anyone tell me? So if z belongs to R, minus minus iz belongs to, so z is in real axis, so minus iz in, it will be in
Real axis also.
no, z is in real axis, so minus iz.
Imaginary axis.
Yeah, so z is in real axis, so minus iz will be in imaginary axis. Okay, so f of minus iz will be again in imaginary axis, because f takes imaginary axis to itself. Okay, so this part will be in imaginary axis, then again multiplied by I. This will give it to, this will send back it to where? Again to real axis.
Real axis.
Yeah, so gz also belongs to R. So by the Swatch reflection principle, by Swatch principle, G is entire and so is F. Clear? So this is true. Now let F says that omega to C is an injective holomorphic map, then F is a closed map. That is, F maps closed set to closed set. So can anyone tell me what is the definition of continuous function? Inverse image of every open set is open, isn't it? Hello? So let us look at the third option. So third option is also true. So basically F inverse will also be holomorphic. Okay, so this is basically inverse function theorem in complex variable. Function theorem for holomorphic functions. Okay. So now F inverse. Now F inverse is holomorphic, means it is continuous. So F inverse image of F inverse maps closed set onto a closed set. So basically what does it mean? F maps closed set.
Closed set
Yeah.
onto closed set.
So this implies F is a closed map. Okay. So third is true. Now let us look at the fourth option. So fourth option is false. So question is, F is a non-constant holomorphic function on omega, then the inverse image of compact set is compact. Okay. So fourth option is false. For this you consider the function fz is equals to e to the power z. So this is nothing but e to the power x into e to the power I y. Now you consider the line x belongs to C such that x is equals to C. So this is basically line parallel to y-axis. Okay. So basically, what is f of L? So f of L is a circle centered at origin and radius e to the power C. Okay. Okay. So let K be that circle. K be the above circle. Above circle. Okay. So F inverse K. Now K is compact, but F inverse K is nothing but here something union of lines. Okay. So one part is L. So you can see that F inverse K is not compact. Clear? Whether this one is clear?
Yes, sir.
Yeah. So fourth option is also false. Okay. Now let us look at the last option. F such that omega to C is holomorphic function such that image is compact set, then F is constant. So we know that every non-constant holomorphic function is an open map. Okay. So fifth option is also false. Oh sorry, this is true. Every non-constant is an open map. So for the image to be compact, this to be compact, F has to be a constant. Okay. So this is true. Now let us look at the last question. Question number 5. So question number 5 is not that much difficult. Okay. So basically, so F says that omega to C is non-zero holomorphic function, means it is not the zero function. F is not identically equal to 0. Okay, is holomorphic such that this F to Z, this is basically Fz into Fz, is basically Fz bar. Okay. Now we need to check these conditions. Okay. So from these conditions, since F is holomorphic, f2z means fz into z fz, fz into fz is also holomorphic. And this is equals to fz bar, that is fz bar is holomorphic. So since fz bar is also holomorphic, what does this implies? This gives us that f has to be a constant. F has to be a constant, isn't it? This is clear. Like you can use the Cauchy-Riemann and you will get.
Yes, sir.
Yeah, so f has to be a constant. So any holomorphic function on omega with its image contained in the real line is a constant function. Okay. So this is true. Any holomorphic function omega with its image contained in the unit circle is a constant function. This is also true. As we have seen that f is a constant function, so this is true. This will also be true. Okay. The function could be a non-constant function which takes exactly 3 values in the complex plane. Okay. So this is not possible. Okay.
The constant function ऐसा कैसे बोल सकते हैं? The function f cube is a constant function.
No, so basically your fz is k. Okay, for z belongs to k, for z belongs to omega. So now fq is what? Fz into fz into fz.
अच्छा, k cube.
So it will be k cube. So it will be constant only.
Okay, sir.
Okay. Yeah. So now this is this is completed. So any doubt?
इसमें last बाकी है ना?
Where is the last one? Yeah, this one. So f could be non-constant function which takes exactly 3 values in the complex plane. So is it possible? So we have already proved that this type of function has to be constant.
Yes, sir. Not possible.
Yeah. Is it clear to you, Rajesh?
Yes, sir, clear.
Okay, fine. So basically what we are doing in this one is nothing but, so since fz is holomorphic, so what will be fz bar? So this is nothing but ux comma y plus I v of x comma y. So what will be fz bar? This will be ux comma y minus I v of x comma y, isn't it?
Yes, sir.
Yeah. So since f is holomorphic, this will satisfy the CR equation. Ux equals to Vy and Uy equals to minus Vx. And this is also holomorphic. So this will also satisfy. So Ux is equals to minus Vy and Uy is equals to what? Vx. Isn't it?
Yes, sir.
Now combining all this, you will get that Ux, Uy, Vx, Vy is 0. So f dash is 0, means f is constant.
Yes, sir.
Okay. So any doubt?
No, sir.
Okay, thank you.
Thank you, sir.
Yeah, thank you. So we will meet in the next
Thank you.
session. Yeah, thank you, Rajesh. Thank you, Dasya. So we will meet in the next session.
Okay, sir.
Okay. So I will close the meeting. Okay.
Okay. Thank you, sir.
Okay.